Remember that G is the center of gravity and M is the metacentric height. The ship in the middle has G positioned below M, that is called a positive GM, and the ship has stable equilibrium. The forces of gravity and buoyancy act to return the ship to the upright condition. We are about to introduce something called GZ and how it acts as a righting lever. The ship on the right has G positioned above M, that is called a negative GM, and the ship has unstable equilibrium. The forces of gravity and buoyancy act to capsize the ship. We are about to introduce something called GZ and how it acts as an upsetting lever. When the ship is heeled, the center of buoyancy moves to B, by the lower red dot, the new center of buoyancy of the new underwater shape. The force acting at center of gravity, G, is still acting vertically downward from the same position. The force acting upward from B is no longer acts in the same vertical line as G, but vertical line up from B is still passing through M. A horizontal line drawn from G to the vertical line from B to M, BM, intersects BM at a point we will call Z. In the previous slide, we saw where Z is located. The distance from the position of G to the vertical line passing through B and M is known as GZ. It follows that lowering the center of gravity would increase the distance GM and would also increase the length of GZ and subsequently increases the righting lever. In this diagram we see GZ as a righting lever when the ship is heeled to the right. Let's take a look at what happens if we start with G above M, a negative GM. When the vessel is heeled, the center of buoyancy moves to B, by red dot, the new center of buoyancy of the new underwater shape. The force acting at center of gravity, G, is still acting vertically downward from the same position, but is pulling the low side downward. The force acting upward from B is no longer acting in the same vertical line as G, but vertical line up from B is still passing through M and is pushing the high side higher, creating a capsizing moment. Here are some key points about stability. Stability is the ability to remain upright and return to the upright position. G must be below M. The distance GM is not equal to vessel stability. It is an indication of initial stability. The true expression of stability is the righting moment. While we know about a moment as an informal unit of time, as in moments later or 1 moment please, here we see that moment can also be something that produces motion, especially around a pivot like a hinge. Is a force with a turning effect. The moment when closing a door is the force used to push the door multiplied by the distance from the hinge where we push it. So a moment is a force with a turning effect. We will look at moments later. First, let us look at righting lever step by step. Here we see the now familiar upright ship with the positive GM that is G below M and also vertically in line with B. Here we see the same ship heeled up to 10 degrees to the right. M does not change for small angles of heel up to about 10 degrees. Likewise, GM will not change for angles of heel greater than about 10 degrees, and crosses the center line at a new position, specific for a given angle, and is no longer considered to be at a fixed point. We saw one example of the metacenter moving to a new position when we looked at angle of lull in a previous lesson. 2 things you will recall if you've been doing these lessons in sequence. The center of buoyancy of the ship moves to the new center of the underwater form, B1 and 2. At angles of heel less than 10 degrees. The upward force from the center of buoyancy passes through the initial metacenter, M. Z is the position where a line drawn horizontally across from G meets the line B1M. Here we see the lever acting downward from the ship's center of gravity, G, to the center of Earth, and upward from the ship's center of buoyancy, B1, through the metacenter, M. To calculate the righting lever, JZ, we need to know the angle of heel in the grams. The righting lever is called the GZ, and GZ equals GMX sine of the angle of heel. For example, the angle of heel equals 10 degrees, the GM equals 2.5 meters, GZ equals GMX sine of the angle of heel, GZ equals 2.5 meters x 0.1765. From tables, GZ equals 0.44 meters. In a stable vessel, the righting moment is equal to the weight of the ship, displacement multiplied by the righting lever, JZ. This is also called the moment of statical stability, MSS. It is expressed in ton-meters. The displacement is obtained from entering the displacement table with the draft, and is equals 500 ton. The GZ from earlier example is 0.44 meters. Moment of statical stability equals displacement x GZ, that is 500 x 0.44 equals 220 ton-meters.